Alright, so here's an exercise which is sort of helping us to get more familiar with normal subgroups and with homomorphisms and stuff like that. So it's kind of neat. Um, let's see here. Thankfully, we know that G is a group already because it was done in a previous exercise, so you don't have to do things like check commutativity or associativity, which is typically really tedious for like more complicated um, definitions of products like we have here. We know that, let's see here, we have an element 1, which is just 1, 0. So we want to prove that K is normal. What does that mean? Claim for all elements 1b in K, and we'll call it AC in G. A here, of course, is not 0. We have AC inverse 1b AC is in K. So here, we also have to recall what is AC inverse. So I don't think we actually, we probably would have derived it in the proof that G is a group, but anyways, let's, instead of showing you how to come up with it, I'm just going to verify that what it is what it is, and you can think about how you would come up with this, but that would take like time and energy, and I don't want to do that. So it's going to end up being A inverse and negative A inverse C equals 1, 0. And I guess we should check the other direction. I didn't write notes about it. I always get... Well, we don't have to check the other because we know this is a group already. I always get confused about that. Like, when do you have to check both multiplication? When do you have to check that, like you could have left inverses and right inverses that are different, and that can happen in like weird things like monoids, I'm pretty sure. But things are fine here because not only is this like we're dealing with like groups, but we know this is a group, so we're good. So anyway, AC inverse equals A inverse minus A inverse C. So let's do some calculations. AC inverse 1b, and we're just gonna straight up calculate this and show that it does what we want it to do. Okay, so that's A inverse is this, and now let's just go ahead and multiply 1b and AC. So we're going to get we're going to get 1 times A, which is A, then we're also going to get C plus B. Now let's all multiply these together. We get A inverse A, then A inverse C plus B, minus A inverse C. And let's see here, the A inverse C's are going to cancel, and the A inverses are going to cancel, so we're going to get left with 1 and A inverse B. And this is in K. So indeed, K is a normal subgroup of G. I learned this triangle thing to denote normal subgroups, and so whatever. I'm getting a call from like a number that's like my own phone number, but like very slightly different, like the first, like same area code and same 3 first numbers. It's really annoying how they do that. I wish they would stop forever. So next, consider the map phi, which will go from the set G to the set R star, given by phi of AB is equal to A. Let's see here. So what do we know? Phi of 1, 0 is just 1, and phi of AB times CD is phi of, let's see here, I won't put too many more parentheses, AC AD plus B, which is just AC, but that's phi of AB, phi of CD, and so phi is a homomorphism. Clearly, kernel of phi is equal to k because the values of phi depend entirely on that first coordinate, and if it sends to 1, then its first coordinate has to be 1. And so by the fundamental theorem of group homomorphisms, G modded out by its kernel is isomorphic to the group that maps into, which is R star with multiplication and an element 1. And there we go. We've finished this proof.